So again, the other topic we were talking about was proof of volume of a sphere, or proof of volume of a semisphere. Here's a semisphere. Now we can start. The center to the side of any point of a semisphere of the sphere. The length is always the radius. In case you don't know that, you can go check online, but you should know that by now. Same thing. So how do we figure out a volume of a semisphere? You want to say we're gonna use the same formula we were using on the volume of a coin? Yes. Let me get a new color. Here. I borrowed this from the library, so nice enough. So we're seeking for disk that's in the sphere, so it's a disk will represent the green pen. So a disk right here, a disk, which is a cylinder we were talking about, with infinity thin, unlimited thinness on the height, dx. So you might want to see the the disk again. I might do it a little bit better this time. So it's a disk, look like this, with a very, very tiny of little bit of the height, and the height right here is dx. Center of a circle, I'm going to call this R1 too, so it's R1, but we might not need it, who knows. And let me make it perfect. Actually, it's perfect now. This is the disk over here. Now we try to find the volume of the disk, because this semisphere has infinite amount of this infinite number of this. We combine together to get a volume of this semicircle. And the formula for the volume formula for a cylinder, again, for this cylinder is the area times the height. The area times the height, and the area is pi r squared. Again, we know pi r squared right here is pi 1, therefore there is r1 squared, pi r1 squared. So what is this? What is the radius? Or in this case, what is r1? What is R1? So, right here we require a little bit of imagination. I always say imagination, because you do really need to sink into this sphere to see it. Let me get another color. Oops. Camera bombs and library students. Let me get blue pen back. So, here is the big circle. This is R. And you can see a pattern already. If the center of the disk is connected to the center of the circle, so they must in the same height. So let's say the distance, the height between the center, the base of the circle, to what? To where the height that disk is x. Here again is x. And since the disk is lighting a point on the circle, let's connect the point of the circle to the center of our circle. So this is x, and this connects to the center of the circle. What's the length of this? What is the length of this? The length of this is r. It's the radius of the big circle. Why? Because we have a sphere, we found the center to every single point to the circle. That's r, just like the other one. That's r. So, since here forms a right triangle, what is r1? Now we apply to the Pythagorean theorem. The Pythagorean theorem say a squared plus b squared equals c squared. In this case, x is a, r1 is b, and r is c. and that it's the same as a square, b squared equal c squared minus a squared, where b is R1, c is big R, the radius of this sphere, and a is just x. Let's take a look at an overview of this right triangle. So you might or might not visualizing there's a right triangle inside of that. And according to Pythagorean theorem right here, we minus a on both sides, right? Minus a on both sides. So b squared, r1 squared, c squared, r squared, a squared. Fair enough. So what is r1 squared? Oops, r1 squared is the square of c minus square of x. So it's r squared minus x squared. And right here, r1 squared. What do we know about r1 squared? If we actually look at this, this is a big R. Oh my god, I'm feeling so bad on this video. But make sure I understand what I'm talking about though. Follow in mind, so r squared, the volume of the center is just r pi r squared dx. So this is pi r squared. I mean, this is r squared, right? R squared. So the volume of this little cylinder, we can say, is pi r squared, which is r squared minus x squared, because pi r1 squared is r squared minus x squared dx. Now this is only just the volume for one cylinder, so it's for one cylinder. We have infinite number of cylinders in this sphere from 0 to r. There we go again, the definite integral. So the definite integral from 0 to r, right? Pi, because we want a constant on the side, r squared minus x squared dx. Fair enough. Then what we're gonna do next? We're gonna take the integral. We're gonna take the integral of this thing. And just keep in mind again, this r squared is a constant. You need it because you don't want to confuse with a variable, because you're not gonna take the integral to 5th dimension, 6th dimension without even knowing that's a constant. So you don't need it. So what is the integral of a constant? That's just going to be the constant times x, right? The integral of a constant is a constant times x, fair enough, minus what is the integral of x squared? That's gonna be x cubed to the over there. Again, you have to know this in mind, that the content of the table of content of derivative and integration and check identity, like bonding to your mind, times pi, because we're using pi times the entire equation. So we move the pi to the integral no matter what. From x equals 0 to x equals r. Fair enough, right? Simple. This what we did is just take the antiderivative of this integral. Right. Now we sub r into the sub r into the x, the 0 to the x if you want to. But you will see. So it's pi times r squared times r minus r to the third over 3 minus the entire equation, minus, because we're packing 0 for r, I don't know if it's necessary, so it's pi times r squared to 0 minus 0 to the cube minus 3, which is just 0, so it's minus 0. So if we simplify the whole equation down, so what we did is just plug in r and 0 for x. There we got this. If I'm going too fast, you can pause the videos. So we get pi times r to the third minus r to the pi times r to the third minus r to the third over 3 minus 0. Cool? So what is pi to the third minus pi to the third over 3? That is just gonna be 2 pi, oh my god, what was I saying? Oh, what is r to the third minus r to the third over 3? It's gonna be 2r third over 3. Right?